Here's 3 sample problems on how to solve diffraction grading questions. The first question that we're going to look at is a student shines a 540 nanometer laser through a 100 lines per millimeter diffraction grating, this one over here, on a screen that is 1.5 meters away. Calculate the spacing of the maxima formed on the screen. So just to remind you, this would be my diffraction grating, okay, and the spacing would be 100 lines per millimeter, okay, so 100 holes per millimeter, and our laser is shining light that is 540 nanometers through that onto a screen, okay, that's my screen over here, and it's going to project a pattern, okay, this will be my central maxima, and then here's all my other maxima that are going to form throughout. Now, with the diffraction grating, the central maxima would actually be the same intensity. I should have drawn them all the same size and not have that large central maxima. But what the question's asking is, what is the spacing between? Okay, just wanted to draw that triangle to get you to remember diffraction. That would be my diffraction angle. And the question is asking us for this spacing. What is x when this is 1.5 meters? Okay, so using all of that, it's a pretty simple question where we just have to apply our knowledge of the diffraction equation. So remember, the diffraction equation is d sine theta is equal to n lambda, and what we're trying to find is x, okay? And so in order to find x, I need to find that angle and then use trigonometry to be able to solve for x. Okay, there's other solutions you can see online that are a lot quicker than this, but I'm going to take us through a little bit of a longer way. So what I want to do is I want to apply this equation to calculate the angle and then be able to calculate x using all these dimensions. So first of all, I need to convert 100 lines per millimeter into d. Okay, d would be the spacing of each individual line. And so what I need to understand is that 100 lines per millimeter is equal to 100,000 lines per meter. Okay, that's important. So the actual width of one line would be 1 meter divided by 100,000 lines, and that would be equal to d. Okay, and then we have sine theta. N, since that's the first order maxima, that's going to be 1. And the wavelength of my laser is 540 nanometers. So 540 times 10 to the minus 9 meters. Okay. By rearranging all of that, sine theta is going to be equal to 540 times 10 to the minus 9 meters divided by 1 meter over 100,000. Okay. And that should give me an angle. So let's quickly do that. All right. So I'm sure that you guys can do this quicker than me. I'm using my iPhone calculator. That's why I'm having a hard time. Okay, so divided by that's going to be equal to 0.054. So theta is going to be sine to the minus 1 of 0.054. Okay, which is going to give me an angle of 3.1 degrees. Okay, so that diffraction angle here is 3.1 degrees. Okay, now using trigonometry, this is opposite, that's my adjacent, I can use tangent. Okay, so then tan theta is equal to x over 1.5 meters. All right, so x is going to be equal to tan theta times 1.5 meters is equal to x. So tan of 3.1 degrees times 1.5 meters is equal to x. And as you can see, I have the answer written here. X is going to be equal to 0.081 meters, which is 8.1 centimeters. Okay, and that's how we would go about solving that type of problem to solve for x. So then I would be able to say that if I measured the distance there, it would be 8.1 centimeters away. And each one of these would be successively 8.1 centimeters away. Okay, so that's the first problem that we're looking at. The second problem, a student shines a laser through a 100 lines per millimeter diffraction grating on a screen that is 1.5 meters away. The student measures a distance of 12 centimeters between the central maxima and the first order maxima. Calculate the wavelength of the laser. Okay, so again, here's my diffraction grating, here's my screen, okay, and we have that middle one is my central max. Okay, so what it said is that the distance between that is 12 centimeters. Okay, so it wants us to calculate the wavelength of the laser. So again, really quickly, we have d sine theta is equal to n lambda. So the question is asking us to calculate the wavelength of the laser, which means d sine theta divided by n is equal to lambda. That's what we're going to be doing. So I have to substitute everything into here. So remember, to calculate d, you can just use what we did in the last question. Okay, 100 lines per millimeter is equal to 100,000 lines per meter. 1 meter divided by 100,000 lines is going to be equal to d. Okay, because it's the same diffraction grating. So 1 meter divided by 100,000 lines times sine theta over n. Now n is going to be equal to 1 because this is my first order maxima. So over 1 is equal to lambda. So what is theta? What is sine theta? So how do we have that? That's 12 centimeters. And remember that it's 1.5 meters away. So we have everything to be able to solve for theta. So again, tan theta is equal to 12 centimeters divided by 1.5 meters. Okay, I'm just going to change that into meters. Okay, and so then theta is equal to tan minus 1, which is going to be, let's quickly calculate that. About 4.57 degrees. Okay, and then if I have that angle, I should be able to then calculate everything else. So let's figure out what the sine of that angle is going to be. Okay, so then I just have to plug this value into there. So then I have 1 meter over 100,000 times sine of 4.57 degrees is going to be equal to the wavelength of the laser. Okay, so sine, 4.57 sine that gives me a wavelength of a laser to be 7.97 times 10 to the minus 7 meters, or 797 nanometers is equal to my wavelength of that laser. Oh, and I had that answer, so that's correct. And then the last question that we're going to look at, a student shines a 650 nanometer laser through a diffraction grating on a screen that's 1.5 meters away. The student measures a distance of 30 centimeters between the central maxima and the first order maxima. Calculate the number of lines per millimeter in the grating. Okay, so here I got a grating, tick, 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 and we don't know the lines per millimeter. Okay, so this would be an experiment where we're trying to figure out how many lines per millimeter are in that unknown grating. Okay, and we have a screen, again, with our pattern that forms on the screen, evenly spaced, okay, and the student goes off and measures that angle. Okay, so this is 30 centimeters, and this is 1.5 meters away. Okay, so in order to calculate the spacing, we got to use that formula again. D sine theta is equal to n lambda. And in this case, we're going to solve for d. So d is equal to n lambda over sine theta. And I need to figure out what that angle is in order to be able to solve everything. So d is going to be equal to 1, because it's the first order maxima, times 650 times 10 to the minus 9 meters, that's 650 nanometers, divided by sine theta. Okay, in order to calculate theta, we go back here and say tan theta is equal to 0.3 meters divided by 1.5 meters. So theta is equal to tan, and that angle is going to be equal to 0.3 divided by 1.5. Second function tan, 11.3 degrees. Okay, so D is equal to 1 times 650 times 10 to the minus 9 meters divided by sine of 11.3 degrees. D is then equal to D is equal to 3.31 times 10 to the minus 6. And remember, for lines per, that's going to give us, that is equal to meters per line. Okay, and we're trying to find lines per millimeter. So first thing I got to do is I got to do the inverse of that. So 1 over 3.31 times 10 to the minus 6 is going to be equal to lines per meter. Okay, so if I inverse that number, okay, I'm going to be left with 301,717 lines per meter. So how do I convert that into lines per millimeter? Okay, well, I'd have to divide that by 1,000. There's 1,000 millimeters in a meter. Okay, so if I divide that by 1,000, I will be left with 301.7 lines per millimeter. Okay, that's the answer. So 0.7 lines, so I would probably round down and say there's 301 lines per millimeter. And that's exactly what the answer is. All right. That's it. So just to summarize, here's just 3 different classic problems for calculations of diffraction gratings. One calculation would be to calculate the spacing of the diffraction pattern that you would see. The second calculation would be using a diffraction grating to calculate the wavelength of a laser. This is often a student's IA. Okay, and then number 3 would be to calculate the actual spacing of lines inside of a diffraction pattern, okay? So for example, your iPhone has pixels. You can use this setup to be able to measure the spacing of pixels in an iPhone. I think that's what Arnav is gonna do for his IA, okay? I had a student last year who took onion root, and onion root has spacings like this in the cells, and was able to actually measure the spacing of the cells using diffraction. So there's lots of cool things you can do with diffraction for IAs and these types of problems. All right, good luck.